Hi there, this is Mr. Deiulis again, and I'm going to be talking to you about vectors today. Vector and scalar quantities, actually. So something that is scalar is something that has magnitude or size, but does not have direction, versus a vector has magnitude and direction. So while speed and distance don't have any reference to a direction, position, displacement, velocity, and acceleration all do. Let me give you an example. Another example of a scalar. What about the Richter scale? If you have an earthquake in California, if something's a 7.9 on the Richter scale, it's a pretty severe earthquake, and it's a Richter scale. It's a scalar quantity. It has magnitude but not direction. The scale refers to how much the ground is vibrating. It goes from 0 to 10 essentially. You can't have a negative value of vibration. So it's only got one direction, really. So it's scalar. Vectors, however, can go in multiple directions. So down here I have a number line. If I say that the heart is where the home is, if I go in some arbitrary direction, you can forget about the number line for a moment. Let's say that this is, at least viewed from above, two-dimensional. If I tell someone that I go 4 miles from home, I'm not telling you in what direction I'm going. So I could be anywhere along that circumference. You don't know. Because all I've done is I've just given you a distance, not a displacement. Because I haven't told you what direction I've gone into. So that would be an example of a scalar. It has magnitude, but not direction. Let's backtrack a little bit. Now that we can take into account some direction, like this number line, what if I start at home and I go my 4 miles in a positive direction? We can consider the positive direction to be, let's say, east, just to keep it along the same sort of directionality here. And then from there, I then go, let's say, 3 miles west, or in a negative direction. And then I finally go 1 mile east, or in a positive direction. What have I really done? Well, in terms of distance, I would just add up all of those values. So I went 4, then I went 3, and then I went 1, and so I went 8 miles total. So in terms of my effort, I can feel that I've gone 8 miles. However, when I'm really concerned about where I started versus where I ended, what is my overall end result? The term actually is called the resultant. And so the resultant is the distance, or I should say the displacement, from where I began to where I ended. And I can show that with a different color. Let me go from where I first began to where I ended, right? Remember that this final one here is where I ended, and what I did was called tip-to-tail vector addition. You saw me actively doing it. I took these arrows and I just went from the tip of one, I put the tail of the next, the tip of one, the tail of the next, until I'm done, at which point I then draw my resultant from the very beginning to the very end, and it shows a physical representation as to how far I really went in terms of displacement. And as you can see, I went in an eastern direction 2 miles. I could do that algebraically as well. I could say that I just simply sum up all the values. So I had a positive 4, then I had a negative 3, and then I had a positive 1. And so when you sum all those together, you get a positive 2 value. This is simply my algebraic sum of those vectors. It's that simple. We just have a graphical representation with these arrows. And so when it's just a one-dimensional like this, it's nice and simple, but we're going to break it down into two-dimensional representations. So now let me show you what happens when we have some sort of two-dimensional vectors happening. So let me draw a couple of arrows to represent some vectors. I'm going to have, let's say, vector A and vector B. And I suppose I actually cheated a little bit there. So this will be vector A, and this one here will be vector B. And so to do the tip-to-tail vector addition, if these are the two vectors that need to be added together, we'll take this one and put it to the tip of the previous, that is in fact vector B. And then the resultant, which I will label with an R for resultant, will go from the very beginning to the very end, and I just like to draw that in a different color. Purple always is good. We'll go from the very beginning to the very end, and that's the resultant. It's that simple. I would like you to notice something. It doesn't matter which one's vector A and vector B, really. I can start off with this one, and then this, and I get to the same spot as if, what if I start off here with the other vector, and then, well, look at that. I end up in the same spot. My resultant is the same no matter which order I put them in. It's the same resultant. I can have a multitude of vectors. Let me just draw some more vectors just randomly. Okay, let's add them all up. My resultant is no longer the same. Let's get rid of it. And again, it just simply doesn't matter which direction I go. Let me go ahead and put my heart where the home is. We'll start there, and let's see where we end up. I'm just going to grab one. I'm going to put, I suppose I have to put that to the back. Get back there. All right. So I'll start at the center there, and I'm just going to go tip to tail vector addition. I'm going to add them up in some very arbitrary order, and I'm going to mark the spot where we end up. Okay, so the star is where we end, home is where the heart is. Home is where we started. You should recognize that it doesn't matter in what order I put these in. Just going to add them together, just going tip to tail, tip to tail. And I'm going to end up at the same spot every time. And my resultant goes from the very beginning to the very end. And again, I could change these around in any way that I wish. Let me put that one back. And let's say that I, one last time just to show it. And there we go. So our resultant is all of those added together. This is known as tip-to-tail vector addition. Okay, so let me kind of break down just back down to two vectors. All right, so starting fresh, let's add these two vectors together. Again, tip-to-tail vector addition, tip-to-tail, and then draw the resultant from the very beginning to the very end, just like so. All right, so that is known as tip-to-tail vector addition. However, there is another method. Let me actually just take that resultant and put it off to the side. So the other method, actually both start at the same spot, essentially. And this is known as the parallelogram method, where I'm just going to draw another arrow that is equal in length and direction to each of these. I'm going to make these dotted, though. And I know this actually isn't as easy to do on paper as it is for me to do with my electronic board here, but I'm going to go tip to tail, essentially redrawing this vector here and putting it to this location. I know that seems like tip to tail vector addition again. And do the same thing here. It essentially is the same thing as tip-to-tail vector addition. You're just kind of doing some extra work, if you will. In this case, you actually kind of can draw your lines extra long as this one here is parallel to this here. So you just draw a line parallel. And then where they cross is going to be where your resultant is. And again, it's going to wind up being the same resultant. Just start from the very beginning to the very end. And that is parallelogram method tip-to-tail vector addition, it's essentially the same thing. It's just that tip-to-tail is a little bit easier. It's not as much work typically, and it's a little bit easier visually, personally, I think. But it's a personal preference, and either one is perfectly acceptable. Now let me go over one little change here. What if I were to say that this is vector A, and of course this is going to be, relatively speaking, vector B. However, I want to know what is A minus B. Rather than adding them, I'm now subtracting them, which this is not terribly typical, but I believe I have seen it actually on the AP test. So here we go. It's pretty straightforward. Let's simply take vector A, bring that over, or in fact, tell you what, I'll copy it and paste it here. So I've got my vector here, and I'm going to do the same thing here. I'm going to copy it and paste it. But since I am subtracting the two, I'm going to take B, and it's effectively now a negative value relative to what it was. So it's now going to be in the opposite direction from what it was, because it is a minus B, and my resultant is now going to go from the beginning to the very end, and that is now the resultant. So that would be a minus B. We simply have to take this vector, and you should recognize that this is essentially the same thing as saying A plus a negative B. So this here, if this one here is B, then this here will be negative B. All right, hopefully that's sufficiently clear, and we'll move on. Let's actually kind of just recap and then end here. So we have the parallelogram method. With the parallelogram method, we simply draw lines parallel to each vector where they crisscross. We will get to the resultant. If you notice, when I showed you the parallelogram method, I did not show you the addition of more than two vectors, which kind of gets me to the point as to why it is that I feel that the tip-to-tail vector method, which works for multiple vectors, is a little bit more comprehensible. So that, rather than parallelogram, would be known as the tip-to-tail method, where you simply just take the tip of one to the tail of the next, and you can keep adding on as many as you want, as for the tip-to-tail vector addition method. This can apply for distances, for displacements. This actually also can apply for velocities as well, even accelerations, but more likely we can use the case of a velocity. And let me finish on that point here, I think. Let's say that you have a plane that is flying north at, let's say, 100 meters per second. It's kind of a slow-flying plane, but nonetheless. If that plane is flying in a headwind, then that headwind, there we go, a headwind of, let's say, 20 meters per second. Then how fast is the plane flying relative to the ground? Well, we would have to draw our resultant, and that would give us a value of 80 meters per second relative to the ground. And that is, we can add up velocities with tip-to-tail vector addition in the same sort of way. What if the wind was in the same direction at 20 meters per second? Then, from the very beginning to the very end, the velocity of the two combined would be obviously 120 meters per second. So we can add velocities with tip-to-tail vector addition. It also gets a little bit more complex than that. Let's say that it's a crosswind. Instead of it, let's say it's going east at 20 meters per second. Then in that case, we would draw a resultant. Let me just label that with a red R here. My resultant, we have the 90-degree angle here. I can find the hypotenuse of this triangle to find the resultant. I could even use some trig to find what angle, how many degrees east of north is this thing moving. in that direction, so it can give some actual coordinates. You may have, if you've ever seen the old movie Airplane, he says, "What's my vector?" Vector? He's talking about what is his speed and direction, hence a velocity. And so the hypotenuse of the triangle would be the resultant. It would be the velocity at some angled direction. Remember that in one dimension, we can add up vectors just like on a number line. That's the easiest way to think of it. And we will then transfer that to two-dimensional stuff. That'll be the next thing that we do. All right, so hope that helps. You guys have a good one. See you later.